All right, this is what we started doing in the last class, operational amplifiers. We started looking at the basics of OpAmp. Even before going into the analysis, I started with the summary, okay? The first thing to remember is that the OpAmp is a 3-terminal device, meaning that there are 2 input terminals and 1 output terminal, okay? And of course, that's not counting the power supplies, plus VCC and negative VCC, okay? The basic fundamental operation of an OpAmp in open loop configuration, okay? When the output is not tied back to the input, that's open loop, right? So what happens is the output is an amplified version of the V input positive minus V input negative. So that guy multiplied by A, where A is the open loop gain, and it's a really, really large number. Then I went on to showing you that the output has some limits. The output actually caps off at a maximum of plus VCC, and it caps off at a minimum of negative VCC. Okay, it does not infinitely increase with increasing input difference. Okay, and then we talked about ideal op-amp assumptions. These are very, very important for this course. Okay, I don't care if you have them tattooed on your head or take them on your forearm or write them down on a notes, does not matter. The important thing is that you should know this back and forth. Okay, the 2 ideal op-amp assumptions are that there is a virtual short. Let me explain what I mean. Okay, the first assumption is that this guy, okay, the voltage on the positive terminal is equals to the voltage on the negative terminal. Okay, it's almost like the input terminals, both of these are automatically shorted. Okay, there is no real connection between them, but they tend to behave as if they were connected. And that's the meaning of the idea, virtual short. The input voltage applied at one node automatically shows up at the other. Okay, remember that, we'll come back to this, virtual short. Okay, the second one is that the input current, the current going into the terminals of the op-amp is really zero or infinite input resistance. Okay, so these are the 2 assumptions. We'll come back to these assumptions, use them over and over again when we are solving our op-amp problems. Then I showed you the graphical representation of the 3 regions of operation. Okay, there is a linear region of operation where the output increases as a function of the inputs. Okay, along the x-axis, I showed the difference between V input positive and V input negative. Along the x-axis is the input. Along the y-axis is the output. You see that at the top and at the bottom, there's a flat region. We call that saturation region, okay, where the output does not change even when the input is increasing. Okay, so there is a linear region of operation, and we like to operate within the linear region. Okay, then we talked about the 3 different configurations in which we can connect the op-amp. The first one is the inverting amplifier, and in this class, for all the different configurations, the output is always tied back to the negative terminal. That's called the negative. Let's see, that's the negative feedback. Okay, there's a negative feedback going on over here. Meaning that a part of the output is connected back to the negative terminal. Okay, that's the idea of negative feedback. Now, What's the idea of inverting amplifier? Inverting amplifier specifically means that this input, the V signal, is applied to the inverting terminal or the negative terminal. Okay, if you look in comparison down below, the one down below is called a non-inverting amplifier. Okay, where the input Vs is going into the positive terminal of the operational amplifier. Okay, what kind of feedback do we have down below? Do we have a negative feedback or a positive feedback?
Is it a negative feedback?
It's still a negative feedback because the output is going back into the negative terminal. See, oops, I didn't want to do that. I wanted to do this. The output is going back and being connected to the negative terminal. Hence, it's still a negative feedback. Okay, it's still a negative feedback. Even with negative feedback, I have a non-inverting amplifier when the input is connected to the positive terminal. Okay, when the input is connected to the positive terminal, I have a non-inverting amplifier. And we'll see how this connection gives us the result that we have here. Then we went on to a summing amplifier. Okay, summing amplifier has more than one inputs. Here I have three, A, B, C, but I can have more. But the idea is when I have three inputs, I know for a fact that the inputs are connected to the negative terminal. Hence, this is inverting amplifier with three inputs. Not only that, is this negative or positive feedback? It still is a negative feedback because the output is always going to the negative terminal. Okay, and in this course, the kind of feedback that we will be seeing is only negative feedback. We will never tie the output back into the positive terminal. Okay, we don't do that in this course. Okay, and then it's also a weighting. This acts as a weighting summing amplifier. This is how far we discussed in the last class. Okay, and these notes really are just restatement of exactly what we saw. Okay, an amplifier with two inputs, a positive non-inverting input shown in blue and a negative inverting input shown in red. Okay, it's a positive supply, negative supply, and then the output terminal. What else? Okay, so the positive input is called the non-inverting input, the negative input is called the inverting input, then there is the output. All right. Okay, of course, there's the positive power supply and the negative power supply. What else? Okay, so here is a 741 practical op-amp. Okay, in good old days, it was used left and right as a building block for many applications. Okay, but now what happened is that this op-amp is mostly used for instruction, class, and lab purposes. Real op-amps are all fabricated inside an integrated circuit on a as a part of a larger chip. Okay, but still, this is a very famous, a frequently used operational amplifier, 741. Okay, 741 is a very popular op-amp. Okay, you'll see this in EEE 108 course. Okay, that's about 741, a practical op-amp. Okay, we looked at the terminal voltages and currents. One of these is called the VP. One of these is called the V negative. Okay, this guy V, let me use a different color. This is V positive or VP. This guy is V negative or V minus. Okay, so there are two input terminals. Their voltages are shown as VP or VN. Okay, what else? Okay, we know about this guy, right? The output is the difference between the two input terminals multiplied by the gain. That's the basic operation of a MOSFET, um, an operational amplifier. Okay, and then of course we do know about this guy. The output voltage can only go so far up, as far up as the positive power supply, and it can go as far down as the lower power supply, negative power supply. And these are the limits, the ceiling and the floor, for how big and small the output voltage can get. Okay, then of course I talked about the two op-amp assumptions, meaning that the output voltage VP, the input positive voltage and the input negative voltage, they tend to copy each other identically. Okay, that's the idea of virtual short. This is rule number one that we will be using. Okay, the second rule that we are going to be using is, let's see, that the amount of current going in to the op-amp in the positive terminal and in the negative terminal is really zero. Okay, there's no current going in to the op-amp terminals. Okay, so we'll use these two rules over and over again. Let's begin them. Let's begin using them. Okay, the first thing we are going to do is to use this to solve what is known as, I don't want to do this problem right away. We'll come back to do this. Okay, I want to start with this guy, inverting amplifier. Okay, inverting amplifier. I gave you in this summary that we expect to see this kind of result here. Okay, the output is the input multiplied by some negative number. Okay, because the output is multiplying the input by a negative number. If the input is this guy, the output is going to be like so, an amplified version. Okay, and an inverted version of the input. Okay, so that's the idea. Let's see if we can do the analysis to understand this. Okay, let's do the analysis to arrive at how we see this V output, V input relationship. Okay, the first thing we are going to notice is notice on the figure that the positive input terminal is tied to ground. Okay, so this VP is really zero. Okay, VP is really zero. So I'm going to call this node as VN. Okay, I'm going to call this node as VN and start by writing KCL at node VN. Okay, was it Diana who asked me in the last class if we were going to use KCL? Was it you, Diana?
No, it was not me. It was another student. I
Okay,
don't remember who though.
okay. So, but indeed, we are going to begin our analysis by writing KCL at node VN. Okay, begin by writing KCL at node Vn. Okay, at node Vn, okay, what are the currents leaving? There is one branch current leaving left. There's another branch current leaving to the right, and then there's another branch current going north. Let's see if we can write the different components of currents here. Okay, the current going left is Vn, minus Vs over Rs. So that's this guy. The current going to the left is Vn minus Vs over Rs. Okay, that's the current going left. What's the current going to the right? The current going to the right is into the negative terminal of an op-amp is IN. Okay, so that's current going to the right. Let me see if I can write it over here. IN plus. What's the current going north? I'm talking about this current right here. Okay, that'll be the voltage at this node minus the voltage at this node divided by RF. Let's see what those values are. It's going to be Vn minus the voltage right here is V0, right? Minus V output, VO by RF. All of that equals to 0. And that's according to the KCL at that particular node. Okay, questions please, questions so far. So this is more or less the general procedure that we will follow when we are solving any op-amp problem. We'll set up KCL equations at nodes of interest. Okay, so now let's see if we can apply rule 1 and also rule number 2. Okay, what was rule number 1? If I go back carefully, okay, if I go back to the rules, let me see if I can right here. And as a matter of fact, I'm going to bookmark that so I can come back to this place. Okay, so the first rule, rule number 1, is that the voltage on the positive terminal, V in positive, is exactly same as the V in negative. Okay, that's the idea of virtual short. What's the second rule? Rule number 2 states that IN going into the positive terminal is exactly same as the I going into the negative terminal. Or I can rewrite this guy as I positive is exactly same as I negative, and there's absolutely zero current going into the op-amp. That's rule number 2. Okay, so let's go back and see if we can apply those two rules over here. Okay, let's see if we can apply those two rules over here. But what is rule number 1? Rule number 1 says that V positive is exactly same as V negative. Okay, because of virtual short. Meaning that whatever voltage is applied on the positive terminal, V positive, that automatically shows up on the V negative. Okay, and what's that voltage here? Do I know a value here for that?
The positive voltage, that's the,
Yes.
or the positive voltage that's to ground, so that's 0.
Thank you. That's to ground. That's 0. So this 0 volts automatically shows up on the negative side terminal as well. Okay, because of the virtual short, the idea of virtual short. So if I were to apply 5 volts here, this would automatically track 5 volts. If I applied 100 volts at the positive terminal, that would automatically show up on the negative terminal. Okay, it's almost like they're shorted together. Even though they really are not, they behave as if they're shorted together. Okay, so that's the idea of virtual short. And I know for a fact that I tied that to ground. Therefore, that's going to appear on VN as well. Okay, so that's the idea of virtual short. Okay, now rule number 2 says the amount of current going in to the OpAmp. That's this guy, okay? That's the current going into the OpAmp. This terminal, IN, is 0, okay? That's rule number 2. IN is I positive is 0. So if I apply these two rules, okay, one of these is going to go to 0 because of rule number 2, okay? This is rule number 2 dictates that the IN is 0. Similarly, VN is going to go to 0 as well. Okay, VN is going to go to 0 because of rule number 1. Okay, remember rule number 1? VP shows up on VN as well. VP is 0 over here. So if I rewrite this equation, okay, it's going to rewrite as VS over RS minus V naught over RF equals to 0. And it's easy to rearrange them such that V output equals to Vs into negative Rs over Rf. Okay, negative Rf over Rs. Okay, so that's the idea, and that's what we were after, right? We wanted to find the relationship between, okay, we wanted to find the relationship between output and input, and sure enough, we got this. Questions about that, please? What questions do you have about this? Okay, so this is an inverting amplifier. Let me tell you again as to why this is an inverting amplifier. The output VO is input multiplied by a negative term. Okay, so when you plot the output and input, the output is going to be an inverted version. If the input is high, the output is low. Similarly, if the input is low, the output is high. It's going to be an inverted version and an amplified version. Does that make sense?
Yes.
Okay, good, good, good. We could put some numbers on this. Okay, we could put some numbers on this. Okay, let's see. Let's see that the RF value is this guy. That's RF because it's in the feedback. It's feeding back. Okay, this guy is RS, meaning that it's in the source side connected to the input source. Okay, RS. Now, how would you find the output voltage here? The output voltage is simply negative RF over RS times the input voltage. Or in other words, V output equals to negative 12 times Vs, where this guy is called the closed loop gain. Closed loop gain. We saw the open loop gain A earlier when there is no feedback configuration. But when there is feedback, when the output is tied back into the input, the gain drastically changes to a constant value RF over RS, negative RF over RS. Okay, so that's the idea of how you would solve for this circuit. Okay, and then of course you can look at the practical limits. What's the maximum and the minimum power supply voltages? Okay, and based off of that, I can calculate the maximum and the minimum values for the input voltage possible. Okay, so on and so forth. Pay attention to this. All we have done is just to plug the numbers in to the equation. Negative, so the equation still is this guy. This is the equation that we derived just now. negative RF over RS times Vs. Okay, so that's the equation. We plugged in the numbers carefully. That's the idea of inverting amplifier. Let's see if we can do another analysis. Let's see if we can do, we'll go to the, let's see if we can go to the inverting amplifier analysis. Okay, let's see if we can go to the inverting amplifier analysis, or I meant the non-inverting amplifier. Okay, let's see. I'm going to copy this guy, and see if I can add a page over here. Okay, and paste it. Now what I'm trying to do is to analyze this circuit. Okay, let's see. This is the circuit of a non-inverting amplifier. This is a non-inverting amplifier circuit. Okay, and then the output that I expect to see, okay, the output that I expect to see is V output. VO should be V input. So the output here, V output, that's this guy, that's VO, okay, should be the input voltage, really VG, okay, which is this guy, times some gain. Remember, the gain is positive, 1 plus RF over RS. Okay, so if you were to plot the input and output waves, let's say if this is your input, the output is going to be in phase but amplified. Okay, the output is going to be in phase but amplified. It's not inverted, right? So this is a non-inverting amplifier. Let's see if we can do the analysis for this guy. Okay, we want to begin by doing the analysis, and like we did in the previous class, in the previous example, I'm going to call this as Vn, and I'm going to call this guy, okay, I'm going to call this guy as Vp. Okay, I'm going to call this guy as Vp. I begin by setting up KCL at node Vn. So the current in that direction plus the current in this direction plus the current in that direction should all equal 0. That's exactly what I did in the last example problem, right? So in order to analyze op-amps, this is always the generic procedure that we follow, okay? Set up KCL at node Vn, okay? Let's set up KCL at node Vn, okay? So there are three currents. The current going to the left is what? Vn minus ground over Rs, because this voltage, that's Vn, minus this voltage, which is 0, over Rs, okay? Plus the current going to the right. What is this guy? This is I sub n, going into the negative terminal of the op-amp, okay? So I sub n plus, what's the current going up? Okay, the current going up through this branch is the voltage at this node minus the voltage at that node by RF. Okay, so that's going to be Vn minus V naught or V output VO by RF. All of that should equal 0. So this is step number 1. Okay, step number 2, let's see if I can apply step number 2, is to apply the rules. There are 2 rules. The first rule is that there is a virtual short, Vp is exactly same as Vn. That's rule number 1. Okay, rule number 2 states IP is In is 0. Okay, so in other words, this guy, rule number 1, if I carefully color code this, you know what, I don't want to do the color coding right here. I'll do this way. So In is 0 because of rule number 2. Okay, rule number 2 says the current going in to the OpAmp terminal is 0. Okay, so this guy In is really 0. Does that make sense?
Yes.
Thank you. Now, how about Vp? How do you find a value for Vp or Vn?
Won't we need to find the voltage drop across RG?
Yes, we want to find the voltage drop across Rg, which would be Rg times I positive, the amount of current going through this resistance, correct?
Yes, because by Ohm's law, V equals IR.
Yes, but what is IP?
IP is
What's the
0.
IP is 0, so the voltage dropped across Rg is what? That's 0 as well.
0.
So in other words, the Vp here is really what I apply without any voltage loss. So Vp is Vg, right? Because there's no current flowing through this resistance, there's no voltage drop. Whatever voltage is applied here shows up at that node. Okay, so that's the idea of applying rule number 2. Okay, so Vp is exactly same as Vg. Okay, and that's exactly same as Vn because of rule number 1. Okay, so here rule number 1 tells me that Vp equals to Vn is exactly same as Vg, right? Therefore, I can change these values to mean that Vn equals to Vg, okay? Because of virtual short. So let's rearrange these equations here. When I plug in Vn equals to Vg plus Vg minus Vo by Rf, all of that equals to 0, meaning V naught over Rf equals to Vg times 1 over Rs plus 1 over Rf. Okay, now I can multiply RF on both sides of the equation to get something that looks like this. V naught, so V naught equals to Vg times 1 plus Rs over Rs. Okay. So that's exactly what we thought we were going to see. Okay. Questions, please. So all we have done is to simply apply the KCL equation and rules, the 1-2 rules, rule number 1 and rule number 2. What questions do you have at this time? Okay, so let's see if we can, so that's the idea of non-inverting amplifier. The output VO is input VG multiplied by some gain. Okay, and again, I think there is an example problem here where we put some numbers. Maybe there is not. There is not. Okay, that's not a problem. Questions, please. So all we are doing in this class is to apply analysis and the rules that we saw in the last class to derive the results that we saw in the last class. Does that make sense?
Yes. I have a question about RG. What is,
Yes.
why is RG there?
Yeah, we could have applied VG directly to the positive terminal as well. Yes. This is, but typically what happens is we may or may not plug this in ourselves. This automatically is associated with the voltage source. Sometimes the voltage sources are not ideal. They tend to carry some kind of internal resistance, and this RG is representative of the voltage source resistance. Okay, so if it were up to us, we can get rid of RG and directly apply VG to that positive terminal. That's a good question. So nothing changes even if we get rid of RG in this circuit. Did that answer your question?
Yes.
Okay. Other questions, please. Okay. All right. So we have been revisiting the circuits that we saw in the last class. Okay. Let me, before we leave this, okay, before I leave this slide, I'm going to show you as to why this guy, okay, I'm going to show you why this is called a non-inverting amplifier, because the input VG is applied to the positive terminal. It's a non-inverting amplifier. Okay, it behaves as a non-inverting amplifier. All right, let's go back. So we're jumping back and forth in the three configurations that we discussed so far. Okay, the summing amplifier. Okay, the summing amplifier. Let's see if we can do the analysis for this guy. Let me copy that. Okay. Would you like for me to do the analysis by hand, or can I annotate it on the slides here?
Would it be okay to do it by hand?
Yes, of course, of course. Let's see, let me add a page over here. Okay, let's see if I can paste it. Okay, Here is what I'm going to do. This is a non-inverting amplifier. This is an inverting amplifier. I'm sorry. This is a summing amplifier. So let me write it as summing amplifier. Okay. Now take a look at this and tell me, is this in positive or negative feedback configuration?
That is a negative feedback.
It's a negative feedback configuration because the output is being fed back into the negative terminal. Okay. Now, is it in inverting or non-inverting configuration?
I think this is an inverting configuration because the voltage source is on the negative terminal.
Correct. It's an inverting configuration because the voltage sources, there are actually 3 of those. They're on the negative terminal of the OpAmp. Remember, they're connected to the negative terminal. Therefore, it's an inverting amplifier and it's in negative feedback configuration. Okay, let's see if we can begin the analysis here. Okay, we always like to do the analysis by identifying Vn. So this guy is V positive. Let me do this. This is V positive, and this node is V negative. Okay, that's V negative. So how do you begin the analysis? You always begin the analysis. Step number 1 is by writing KCL at node Vn. That's what you did in all the 3 problems, in all the 2 cases, in the previous 2 cases, both of those cases. Okay, that's step number 1. So what is step number 1? There are different currents that are leaving are 1, 2, 3. Okay, the current going left is actually the sum of 1, 2, and 3 currents. Okay, so this node Vn has 3 currents going left, 1 current going north, and 1 current going east. Let's see if we can set up those currents. What's the current going in the topmost branch? Okay, and I'm going to call this as IA. The current going in the middle branch is IB, and the current going in the left branch, bottommost branch, is IC. So IA plus IB plus IC plus IN, that's the current going right, plus IF, that's the current going north. That equals 0 is what my KCL tells me. Okay. Let me see if I can set up those currents. Okay. Let me set up those currents. The current going left, IA, is Vn minus, so that's the voltage on this node, VA, or Vn minus the voltage on this node. So this guy is Vn, this guy is VA. Remember, I'm applying VA over here, over RA. Plus, what's the current IB?
That would be Vn minus VB over RB.
Correct. The same with IC as well, right? Vn minus Vc over Rc. Okay? Plus, then there is In. Plus, what's IF? What's the value of IF?
That is Vn minus VO over RF.
all of that should equal 0. Okay, so this is my step 1, KCL at node Vn. What's the step 2? There are 2 rules, right? OpAmp problem solving is all about applying those rules. You apply the same rules over and over and over again. What are the 2 rules? Rule number 1.
That was the virtual short.
Thank you.
And then rule number 2 is that the current is 0.
The current going in IP is IN. All of that is really 0. So rule number 2 is really easy to implement. That's this guy. All of that equals to 0 because of rule number 2. Okay. How do you apply rule number 1?
That was the the voltage on the positive terminal was equal to the voltage on the negative terminal.
VP equals to VN. So that's this voltage. The voltage on this terminal shows up on this terminal as well. Okay, what's the consequence of that?
So because VP is tied to ground, then the voltage there would be 0. So then VN would be 0.
Thank you. Thank you. So all of this will exactly equal ground. So if I am to apply that in this equation above, Vn goes to 0. This Vn goes to 0. And this Vn goes to 0. All because of rule number 1. Okay, rule number 1 tells me that Vn really tracks Vp, which is tied to ground. So if I rearrange this equation from the top, it's going to write as negative Va over Ra plus negative Vb over Rb plus negative Vc, really? Negative Vc over Rc plus, now this guy was 0 as well, right? Plus negative V naught over Rf. All of that equals to 0. You rearrange this equation, what you will get is exactly what we discussed earlier. Let me go back. So here is the idea, Vf, V naught, you rearrange this equation, what you will see is this guy, okay? When you rearrange the equation, you will see that the output, okay? Sorry about that, sorry about having to go back so many slides, right here, okay? This is the exact same configuration that we are looking at. VA, VB, and VC are 3 inputs connected. You rearrange, you'll get back VA times negative RF over RA, VB times negative RF over RB, and VC times negative RF over RC. This is what you will see in the summing amplifier. Okay, summing amplifier, weighted summing amplifier. Questions, please. Questions so far? Okay, so that's exactly what you will see here. V output is negative RF over RA times VA plus negative RF over RB times VB plus negative RF over RC times VC. Make sense?
Yes.
Okay, so that's good. So you can put some numbers into this. Okay, you can plug some numbers into this. Maybe this problem. Okay, this example does not talk about does not show some numbers, but it's easy to see this. Okay, plug some numbers in there. What else? I think I left out one amplifier, the difference amplifier, somewhere in here. Let me see if I can go back to that. Is it this guy? Okay. Take a look at this. Okay. Take a look at this op-amp circuit and tell me how it is different from what we have seen so far.
There is a voltage source on both the positive and negative terminals.
Thank you. Earlier we had a voltage source just on the positive terminal or just on the negative terminal. But in this case, the voltage source is applied both to the positive terminal and another voltage source to the negative terminal. Very well. How do you expect the output to be? Okay, so it should act as an inverting amplifier from this to this input, and it should act as a non-inverting amplifier to this input. Okay, so what you should expect to see probably is VA is multiplied by the gain of this guy, the negative gain. There is some negative gain, okay, and VB is multiplied by some positive gain. Okay, so because VB is tied to the positive input terminal, it should be amplified by a positive gain, and VA should be multiplied by a negative gain. So what do you have in effect? VB is weighted by some gain minus VA, that itself is weighted by a gain. So in effect, you have VB times X alpha minus VA times beta. So it's some kind of an inverting weighted difference amplifier. Let's see what we have here. Okay, when we solve the equation, what we will see is that sure enough, VB has a positive gain. Remember, the exact same gain that we saw for a non-inverting amplifier, 1 plus RF over RN. And this guy, let's see, VA is multiplied by a negative gain. Okay, so in effect, what you have is VB minus VA by applying different weights. Does that make sense?
Yes.
Okay, so this part I'm not going to solve using hand. I'm just going to annotate on the notes, if that is okay with you. Or
Yes, that's fine.
if you prefer that I solve it by hand, that's fine too. But I think I want to do some example problems in whatever little time we save by not drawing it on paper. So here is the idea. Okay, and you should be able to solve just by observation anyways. So let me show you a preview of how you should do this. Okay, Vn should really be Vp, which is this voltage. So that exactly should equal Vb. Okay, Vn should equal Vb because this Vp is Vb. Okay, rule number 1 says that Vp should equal Vn because Vp is tied to Vb. Both Vp and Vn should equal whatever voltage is applied to one of the terminals, Vb. Okay. All right. So the first step would be to set up KCL at this node. I want to set up KCL at the Vn node. So according to that, you would see three currents, one current going left, one current going right, which is zero anyways, and then one current going north. Okay, so let's see if we can set up the KCL. Sure enough, there is one current going left, Vn minus Va by Rn, that's this current. Okay, one current going to the right, okay, that's this current. Okay, and then one current going up. Okay, that represents this guy. Three currents at that node right there. Okay, so corresponding to those three currents, I have Vn minus V0 over Rf. Now, rule number 2 tells me that this guy, In equals to 0. Okay, similarly, rule number one tells me that Vp equals to Vn equals to Vb. So in place of Vn, I'm going to plug in Vb. Okay, in place of Vn, I'm going to plug in Vb. Does that make sense? Everybody with me?
Yes.
Okay, that's all there is to it. In place of Vn, I'm going to plug in Vb. Okay, wherever I see Vn, I'm going to plug in Vb. That's because of rule number 1. Okay, now I made In equals to 0. That's because of the rule number 2. Okay, that says the current going into the op-amp is 0. So this guy is 0. Okay, so using that, rearranging the equation. That's all there is to it. Rearrange the equation. Okay, and I'm surprised I let In stay in the equation for so long. I should have gotten rid of that already. Okay, so notice that In is 0. Okay, I can completely get rid of that from the equation. Then V out is going to be Vb times a positive gain plus Va times some negative gain. Does that make sense?
Yes.
Okay, so the general procedure for solving any op-amp, and once you have that algebraic or analytical expression, you should be able to plug the numbers in here and then see the final result. Okay, the general procedure that we have been following is very, very similar in all the circuits. There's very little reason to want to have to memorize any configuration. Okay, we don't have to memorize anything. We simply apply the node analysis, KCL, at node Vn, okay, plus the rules. That's all there is to it. Okay, but after you solve enough number of problems, once you solve enough number of problems, you'll end up in a situation where you cannot forget, even if you wanted to. V output is VA times minus RF over RS. This is an inverting amplifier. Okay, V output equals to Vs times 1 plus RF over RS. This is a non-inverting amplifier. Okay, if you have more than one inputs on the inverting amplifier, you have just 3 of those terms. That's all there is to it. There is an inverting amplifier, there is a non-inverting amplifier. How do you arrive at these results? Just simply by applying KCL and the rules. So you don't want to memorize them. You simply want to be able to derive everything from the first principles. Okay, op-amp problems is all about KCL. and the two rules. Okay, I'll say this one more time. Okay, just so you're not, the problems may look very, very daunting, intimidating. Don't be deterred by it. Don't be intimidated. OpAmp problems. Simple solution is KCL at node VM. Okay, that's step one. Step number two is applying rules. Okay, rules 1 and 2. That's all there is to any kind of op-amp problem. Okay, let's see if we can look at some examples. Maybe I have come prepared to do some examples, maybe not. Okay, let's see. Okay. Okay, I'm going to give you a circuit, okay, and have you solve that. Okay, how about we go further down and look at something like this, the difference amplifier, this guy. Let's take a look at this guy. Let's copy that. Okay, I'm going to add it over here, add a page over here. Okay, what I want you to do is to analyze this circuit. Analyze this op-amp circuit using the two steps that we discussed. Okay, this is slightly different. It's not terribly different. It's very, very small modification of what we already saw earlier. Okay, I showed you how to solve when there is an input VA and an input VB without the additional resistance. Okay, so take a minute to solve this circuit using the two steps that I showed you. What were the two steps again? Let me go back. Step number one. Oops, dang it. Step number one. Okay, is to set up KCL at node Vn. In this case, node Vn is this guy, right? At that node. Okay, that's Vn. Okay, then step number two is about applying the two rules. Okay, take about 5 minutes to see if you can solve this. Okay, give me a second. Okay, let's begin. Any volunteers to help me get started?
I've done the nodal analysis at VN.
Okay, so let me begin. KCL at node Vn. Okay, yeah, help me there.
Okay, so I have Vn minus VA over RA.
Yes, that's the current going left. Okay.
Then plus IN plus Vn minus VO over RB is equal to 0.
Okay. That's step number one, right?
Yes, and then I know that Vn equals Vp, but I'm getting confused a little bit with how to analyze the positive terminal.
Yes, yes. It's simply it's simplified by observing that Vp is a voltage division of VP. That's all there is to it.
Okay, I see that.
Okay, now once you have VP, you should be able to apply VN. So the idea is, now there was no current earlier going into IP, VP, so there was no voltage dropped across this resistance. But now it's a little different. There is a path from this source down to ground. So the current going in here, I, B, that current is VB over RD plus RC. Now what's the voltage drop? Because there is some current going in here, IB, simply multiply that by RD to get the voltage drop VP. Okay, so all I have done is observe that VP is a voltage division applied to VB. Okay, that's all there is to VN. What else? So that's observation number one. This is rule number one, tells me that VN equals to VP, both of which are a voltage division. Okay, what's the next rule?
That the current at the positive and negative terminal are equal to 0.
This current IN, this is equals to 0 because of rule number 2, which is infinite input resistance. Okay, rule number 1 tells me, because of virtual short, that Vn equals to Vp. So now I can plug in these values. Vn is Vp. Is once I plug that in, okay, I'm going to get an expression that looks like this, and I leave that as an exercise for you. Okay, I'm not going to manipulate because it's just algebraic manipulation. The key here is to remember that Vp is simply a voltage division between Rd and Rc. Okay, so once you notice that and plug in Vn equals to Rd over Rd plus Rc times Vb, you plug that into the equation, this equation over here, you should get a result. Okay, V output, if you rearrange this, V output is going to come out to Va by times negative Rb over Ra. Okay, negative Rb over Ra plus Vb times Rd over Rd plus Rc times okay, this multiplied by 1 plus Rb by Ra. Is everybody with me?
Yes.
Okay, good. Okay, so this is still the difference amplifier. Remember, the input VA is multiplied by a negative gain. VB is multiplied by a positive gain. So all you have to notice is this is very, very similar. If you go back, this is very similar to the difference amplifier. Let me go all the way back. I'm sorry for the back and forth, but I'm trying to illustrate a point here. So if I go back to this, somewhere in here, okay, see that VB, let me copy this guy actually. I'm going to copy this. Okay, a difference amplifier. The only difference is that there is no RB term over here, RC or any of the additional resistance here is missing. That's the only difference. Okay, so now if I go back to the circuit, and paste it over here, paste this guy. Okay, so tell me, nothing is different. This VA is right there, multiplied by negative RB over RA term. So VA multiplied by some negative term, followed by VB multiplied by 1 plus RB over RA. The only thing that has ever changed here is this guy. Okay, this guy, meaning that it's a voltage division. Okay, there is an extra resistance corresponding to that. There is a voltage division. But if you ignore that guy, or if you see that as simply a voltage division, nothing else is changing in terms of the difference amplifier. Okay, there are two input voltages you're applying. VA is applied. So let me intuitively provide you an information, some insights into what is going on. Okay, so I'm applying a positive input voltage. I'm applying a voltage VA to the negative terminal, and I'm applying a voltage VB to the positive terminal. So there is an inverting and non-inverting, both of these happening at the same time. Okay, as a result of that, see what's happening. The output is the applied positive VA that is applied to the negative terminal is inverted and amplified. So that's inverting amplifier because it is connected to the negative input terminal. And there is the non-inverting amplifier connected to the positive terminal. And that's all there is to it. Make sense?
Yes.
Okay. Questions, please. What questions do you have at this time? Okay. Let me see if I can solve one problem. Okay. Let me see if I can pick a problem that appears a little complicated. Okay. The difference, it's still the difference amplifier. Okay. Let me see if I can delete this page. We have time for at least one problem. So let's see at the very end, I'm going to add an example problem. Okay, I'm going to add an operational amplifier that looks like so. Okay, let's see, here is my OpAmp with a negative terminal and a positive terminal. Okay, let's see if I can do this. Okay, and then there is this guy. Okay, and then of course there is three inputs going in here. Maybe two. And there is a feedback. Okay, this is so you're asked to find out VO. Okay, and you're given numbers here. This is 20 kilo ohms. And then VA is up high. Okay, this is 18 kilo ohms. VB is over here. This guy is 30 kilo ohms. VC. And then this guy is 20 kilo ohms. VD over here. Okay, And then of course there is 20 kilo ohms applied to this, and 180 kilo ohms applied right here. Okay, that looks quite interesting. Okay, there is this guy, one node over here, there's another node over here. So these are the annotations that I am making, not given. Okay, so there is, how do you solve this problem? Okay, solving this problem still involves the exact same steps that we discussed so far. So let's identify VP and VN. Okay, VP and VN, these are identified as my nodes here, VP and VN. Okay, now I'm going to step one is always about KCL at node VN. Remember, KCL at node VN. Let me set up KCL at node VN. Okay, at node Vn, if I call this as IA, call the current, this guy, as IB, okay, and call this current as, that's the current going into the right of the branch, right of the node, IN, and then this current as IF, okay? So that's this node right here, okay? At that node, there are two branch currents leaving towards the left, one going to the right and one going up. All right, let's see if I can do this. KCL at, everybody with me so far?
Yes.
So KCL at node N would be Vn minus Va over 20 kilo ohms plus Vn minus Vb over 18 kilo ohms plus In that's going towards the right, which is zero anyways. We have seen this In only go to zero over and over and over again, plus Vn over 180 kilo ohms. All of that equals zero. Does that make sense?
Yes.
No, it shouldn't. There's a mistake in here.
Oh, yes. Vn minus Vo over 180 kilo ohms.
Correct. That's Vn minus Vo. That's the current going north. Okay, so that's step one. What's step number two? So let me see if I can do this. Step number two is to apply the rules. Okay, the rule, let me be, rule number two tells me that In equals to Ip equals to zero. So the first step is to make this guy go to zero, rule number two. Okay, rule number two. Now, if I know rule number one tells me Vp equals to Vn. Okay, so if I know the value for Vp, I should be able to calculate, I should be able to plug that in to the equation here. Let me call this equation number one. Okay, now if I know the value of Vp, I should be able to calculate the value of Vp and Vn. Okay, let me copy this over again. Okay, copy this onto the next page. Okay, so the question is, how do you find Vp? Let's see, I'm going to use this color. How do you find Vp? Any suggestions?
Well, I know that there's a voltage division with VD. But I'm not sure how to take into account VC.
Yes, so it appears that there's more at this node VP, there's more than one or two resistances. So we may have to apply a little bit of KCL at node VP. Okay, if we apply KCL at node VP and add all the currents leaving this branch, so let me annotate them as IC, IB, I meant ID, and I don't know, I want to call this as I South. Okay, just an arbitrary name. Let's see if we can apply KCL at node VP, just so we can get an expression for VP, because it appears there's more than one sources. So it's not, I can't do that by observation. So by applying KCL at this node, okay, VP minus VC over 30 kilo ohms, okay, plus VP minus VD over 20 kilo ohms plus VP over 20 kilo ohms. All of that equals 0. Now we should be able to factor in VP, factor out VP, and add 1 over 30K plus 1 over 20K plus 1 over 20K. Okay? And take the VC to the other side, VC over 30K plus VD over 20K. Okay, so it's a matter of rearranging the equation. Once you do that, you should be able to see that VP becomes 1 over 4 times VC plus 3 over 8 times VD. Okay, so this is an expression for VP. Okay, let's see. This is an expression for VP. Let's call this equation number 2. Okay, now what we can do is to plug this value of VC back into equation 1 right here. Okay, back into this equation, equation number 1. Okay, in place of VN, I'm going to plug in VP. In place of VN, I'm going to plug in VP. In place of VN, I'm going to plug in VP. Okay, I can do that. Or it's only going to make the equation so complicated. So what I will do is, if there is a problem that specifies a value for VC and a value for VD, I'm first going to simplify VP to be some number, some known number, okay, depending on the problem. And it's easier for me to plug in a number back into the equation above rather than these complicated looking terms, okay, just so it's easy to read. But you get an idea on how to solve this problem, right? So if I give you a value for VP, if I give you a value for VA equals to 1 volt, VB equals to 2 volts, VC equals to 3 volts, and VD equals to 4 volts. And I ask you to find out VO. Well, the first thing you would do is to calculate the value of VP. VP is a fourth of VC, which is 3 volts, plus 3/8 of VD, which is 4 volts. Okay, so whatever this comes out to be, you plug that number in, okay, to VP, you get some number there, 3/4 plus 1/2 of 3. So this is 0.75 plus 1.5, how much ever that comes out to be. So this number, so this may be 2.25. You plug this number 2.25 volts back into the equation here. Okay, you plug in VP is 2.25. Okay, and VA, the value of VA is given to be 1 volt. You plug in all the numbers. So it's as simple as plugging in the numbers into these equations here. And then you should be able to give me a value for VO. Okay, so if you do that, you'll see that for these values, okay, for these values of VA, you should be able to calculate the value of VO, the output, to be 16 volts. Okay, if you apply an input VA of 1, VB of 2, VC of 3, and VD of 4, your VA should be 16 volts. Does that make sense at all?
Yes.
Okay, questions, please. So
The
all we
problem,
have done, yes.
just the problems that we work on, they will be like this. So we'll need to like sort of analyze what is taking place on the positive terminal.
Sometimes, yes. Sometimes most of it goes by observation. In the back of your mind, you're always trying to apply KCL at node Vn. And in order to find Vn, you need to know Vp. So if it means you have to do a little bit of analysis to do Vp, so be it. You have to dig in to find the value of Vp. What you said is exactly right. So sometimes you may have to do an analysis on the positive side to find its value. Once you find that value, you know Vn. And once you know Vn, it's just a matter of rearranging the KCL at Vn. Did that answer your question?
Yes. So the trick is really just knowing the rules and then being able to recognize other techniques to apply.
Thank you. Thank you. The trick is about applying the rules, rule KCL at Vn and the two rules. And then if there is a little bit of digging that you have to do about VP, that's what you have to do. Okay. If you want, we can come back on Monday. We can cut back on the time that we spend on chapter number 6 because it's a really easy chapter. Or how about I have some, let's see, just give me 1 second. So I'll pause the recording. I'll stop the recording. You know what? No, we let other students know as well. How about by a show of hands, how many of you would want to have some office hours tomorrow, Friday, okay, July 31st from 8 to 9 a.m. So we can go over some OpAmp problems if you have some questions about that or any other questions. Okay, okay. We have about 1 or 2 students who are open to the, yeah, we have about 2 students who want office hours. So I'm going to be at this same Zoom location, 8 to 9. Okay, 8 to 9, let me say this. So for those of you who are present here, okay, Friday, July 31, 8 to 9:35 a.m. office hours. Okay, so I'll see you folks tomorrow. And if you have some questions that you want to talk to me about in one-on-one basis, I'll be able to arrange a private session with you and address any of your questions. Okay, I'll see you folks tomorrow, those who care to attend the office hours. If not, I'll see you folks back on Monday. What I strongly advise you to do is to work on some OpAmp problems, just so if you're stuck somewhere between now and Friday, we can address those questions tomorrow. Okay, see
Have a
you
good day.
folks tomorrow. Take care.